So in this reaction, you're starting with an alkene. That's always a sign that you are doing an addition reaction. That double bond, that extra second bond, that pi bond, is extra molecular glue, extra electrons, which is molecular glue that you can use to add things onto that molecule. So let's say you're given a couple molecules here and you had no idea how they would react. And so if that ever happens, whether it's in this class or in another class, what you always want to do if you ever feel stuck is to look for the nucleophiles and the electrophiles. 95% of reactions happen because opposite charges attract. And the technical term for those negative charges are nucleophiles. You could recognize nucleophiles because they'll have a full negative charge, a partial negative charge, a lone pair, or a pi bond. And you could recognize electrophiles, which is the fancy term for positive charge, because you'll have either a full positive charge or a partial positive charge. So 95% of reactions happen because opposite charges attract. Nucleophiles attack electrophiles. And so if you're ever unsure about how two molecules may react with each other, identify the nucleophiles and electrophiles. There's a 95% chance that the reaction is going to happen by the nucleophiles attacking the electrophiles. So my recommendation is not to sort of stare at the molecules until it pops out at you, but instead to work methodically, one molecule at a time, one feature at a time. So let's start with this molecule on the left and ask ourselves first, do you see any nucleophiles there? Do you see any full negative charges there? No, they would be written in. Do you see any partial negative charges in this molecule? No. You get partial negative charges when you have really electronegative atoms, like nitrogen, oxygen, fluorine, chlorine, or bromine, or atoms with very low electronegativity, like metals, that give their electrons away so that anything they're bonded to are slightly negative. So because we don't have any atoms with extreme electronegativities, metals, very low electronegativity, or nitrogen, oxygen, fluorine, chlorine, or bromine, very high electronegativity, because we don't have either of those, we don't have any of these partial negative charges. Next factor, do we have any lone pairs? No. And then finally, do we have any pi bonds? And we do. So that pi bond is not, you wouldn't want to see that as just a unique thing on this unique molecule that's unrelated to everything you know. Rather, you want to see that as a conceptual unit. That pi bond is really a nucleophile, and it's going to do the same things that every other nucleophile you've seen has ever done. It's going to attack electrophiles. Let's stick with that molecule and look for electrophiles. So we'll work one factor at a time. Do we have a full positive charge here? No, that would be drawn in. And do we have a partial positive charge here? No. The partial charges happen when you have atoms with very different electronegativities. So if you have a very electronegative element, like nitrogen, oxygen, fluorine, chlorine, or bromine, it'll pull electrons to itself. So for example, like in water, that oxygen is really electronegative. It'll pull electrons to itself and become slightly negative, and anything it's bonded to loses those electrons and becomes slightly positive. So that's where you get these partial charges from, atoms that have very big differences in electronegativity. And the ones you really have to watch out for are nitrogen, oxygen, fluorine, chlorine, bromine. Those are in the top right. Electronegativity increases as you go up into the right. And then the other ones you have to watch out for are metals, which are sort of on the left side of the periodic table. And they have just such low electronegativity, they'll give their electrons away, and whatever they're bonded to will become slightly positive. So because we don't have any of those in this case, we don't have to worry about those partial charges, we just don't have them on this molecule here. So even though you may have never seen this molecule before, you now, because you're not looking at it as an individual thing, but as a conceptual unit, you now are able to figure out all the ways that this can react. This can react like a nucleophile, and that's it. There's no electrophile in the molecule. So the only thing this is going to react with is with positive charge. So then let's play the same game with the other molecule. The other molecule we have here is hydrochloric acid, HCl, that's stomach acid. And we're not going to look at it and wait for things to pop out at us. Rather, we're going to work step by step, one feature at a time, through the nucleophiles and electrophiles. Do we have a full negative charge here? No. So it would be drawn in, but even if it weren't drawn in, sometimes it's not drawn in, and you would recognize it because you have a metal and a non-metal. So these metals have such low electronegativities, when they're bonded to something that has a really high electronegativity, it just gives its electrons away. The more electronegative element doesn't share the electrons at all, it just steals them. And so you get elements with full charges on them. So anytime you see a metal bonded to a non-metal, you'll have that ionic bond. And that's really the definition for a salt. A salt is just an ionic compound, any ionic compound that's being held together because of those charges on those ions. Remember, ions are charged atoms. So we don't have any metals and nonmetals here, so we don't have a full negative charge. How about a partial negative charge? We do, because we have one of those really electronegative elements, right? In the top right, we have nitrogen, oxygen, fluorine, chlorine, and bromine. Those elements are really electronegative, so they pull electrons to themselves, become slightly negative, and anything they're bonded to loses those electrons and becomes slightly positive. So we do have that slight negative charge there. Do we have any lone pairs? That's the next factor, and we do. We have 3 lone pairs on the chlorine. So it's another sign that that can act as a nucleophile. And then do we have a pi bond anywhere? We don't. We can do the same thing, going one factor at a time with the electrophiles. Do we have any full positive charges? No. Do we have any partial positive charges? We do, because of that chlorine and the big differences in electronegativity that it has between the chlorine and the hydrogen. So without having memorized anything, just having applied the concepts we've been working with for a while that were first introduced in Chapter 6, we've identified the nucleophiles and electrophiles, and we know how these molecules now are going to react. The carbon chain has to act as a nucleophile. Nucleophiles attack electrophiles. Opposite charges attract. And there's only one electrophile for it to attack on the other molecule. It's the hydrogen. So that nucleophile is going to attack that hydrogen. Hydrogen can only form one bond. So if it's going to form a new bond, the bond it has to break. Those electrons will go to the most electronegative place nearby, which is the chlorine. And so you can see the step that has to happen here in terms of curved arrow patterns is a proton transfer. We're going to move that H plus from the HCl onto the carbon chain. And it's going to change the stability of that molecule a little bit. Okay. So when you are drawing these mechanisms, once you've figured out what curved arrows you have and you've drawn them in, and remember, curved arrows show the movement of electrons, so the tail always has to start at either a bond or a lone pair. It's never going to start at an atom, and it'll always point to the positive charge it's attracted to. But once you have those curved arrows drawn in, you really copy the molecules, and anything that's not touching a curved arrow is going to stay exactly how it is. Anything that is touching a curved arrow, of course, will change. So, for example, this bond between hydrogen and chlorine is at the tail of a curved arrow that's going to move. Where is it going to go? It's going to go onto the chlorine as a lone pair. So chlorine will have an extra lone pair there, and that will give chlorine a full negative charge. Chlorine is in group 7A, minus 8 dots, 0 lines, gives you that -1 charge there. And this is the formula for formal charge from Chapter 1. So if you're not recognizing that, you might go back to Chapter 1 and review the formal charge. And the video's there for it. So then you're going to have this hydrogen, and it's going to be attaching to this carbon chain. But there's a little bit of an ambiguity here because we have 2 carbons in this pi bond. The pi bond is going to both of them. But the hydrogen is only going to attach to one. So which hydrogen does it attach to? Well, we're scientists here, so if we are ever unsure of something, we will do the experiment and think about the results. So let's think about hydrogen attaching to each of those carbons. Let's say the hydrogen goes to the carbon on the far left. That's one possibility. Now notice, when the hydrogen goes there, if you compare these structures, this carbon had the electrons, now it does not. And so that carbon would end up having a positive charge. And if you wanted to, you could draw the hydrogens in and figure out the formal charge. So for example, there's a hydrogen here, there's only one, there's still only one, so carbons in group 4a minus 0 dots, 3 lines, gives you that +1 charge on that carbon. So that carbon becomes a carbocation. Alternatively, you could imagine the hydrogen going to the other. You could imagine that hydrogen that's being attacked in the proton transfer going to the other carbon in the double bond. And so now the carbocation would develop on the other carbon. So these are the two possibilities, the two places where the hydrogen can go, and the two products you would get in those cases. And if you think about carbocation stability, you'll see that only the molecule on the left would be formed. Because here you have a secondary carbocation, and in the molecule on the right you have a primary one. And the secondary carbocation is more stable. So if I'm saying this and you're thinking, oh man, I don't remember stability of carbocations, you'd want to go back to chapter 6, where there are videos devoted to just discussing the stability of carbocations. But here, because the more substituted carbocation is more stable, that's the main product you're going to get. And in fact, even if this other product tried to form, you would immediately have a carbocation rearrangement, and it would just leave you with this other product. So effectively, the only product you get is this more substituted product. This scenario develops or happens pretty often. When you add hydrogen and something else, if the double bond is not symmetrical, the question arises, where does hydrogen go and where does the other thing go? What we've just seen is that if you add hydrogen first, so that you form a carbocation, the hydrogen will always go to the less substituted carbon, so that you'll get the more substituted carbocation, right? So if you were to think about the two carbons in the original double bond, you can look at them and say this one at the end is primary, the one in the middle is secondary. Where is hydrogen going to go? It's going to go to the less substituted one, so that you can form the carbocation on the more substituted one. Now that only happens if you have a carbocation in the mechanism, and the name for that is called Markovnikov's rule. So this is called Markovnikov addition. And if you look at the reaction list that's posted for this chapter, in the notes section at the right of each reaction, you'll see the word Markovnikov appear next to some reactions. And what that means is that the hydrogen for that reaction will always go on the less substituted carbon. And the other thing will go on the more substituted carbon. That's what Markovnikov addition means. So here, we've added that hydrogen. This is the molecule you'd be left with, like we saw. And so now, let's think about how this might react. Now, before the nucleophile attacks, anytime you form a carbocation, you have to ask yourself, will it rearrange? This was the more stable carbocation that could form on the two atoms in the double bond. But is it the most stable carbocation that can form nearby? So sure, the carbon on the left is primary. This carbon is only bonded to one other carbon. But the molecule on the right is bonded to 1, 2, 3, 4 other carbons. That carbon is quaternary. So that carbocation would actually be more stable if it were there. So after this Markovnikov addition, we're going to have a carbocation rearrangement. So we're going to move things around on this one molecule. So when you have a carbocation rearrangement, you look at that more stable position, and you're going to move the smallest thing that's there. So if there's a hydrogen there, that's what's going to move over. Of course, on this quaternary carbon, there is no hydrogen. So the next smallest thing is going to move over, and that would be a methyl group. Remember, curved arrows show the movement of electrons. So the tail of the curved arrow always has to start at either a bond or a lone pair. So we're going to have the tail of the curved arrow starting at the bond of the methyl group that's moving, and the head is going to point at the atom that has the positive charge. So that's our carbocation rearrangement. So when you're drawing the product of that, you keep anything that is not touching a curved arrow just how it is. And so we're not going to change these methyl groups here. We're not going to change these carbon chains. What we are going to change is this methyl group that's moving. So this methyl group is going to move over, and it's going to be on that carbon there. Now when that happens, these electrons are going to push each other apart a little bit. Here, they're going to push each other apart a little bit, and that other methyl group is going to be here. It's going to just spread out a little bit because it's trigonal planar now. Now this positive charge is there where the electrons are missing. The other thing I'm going to do here is I'm going to erase the hydrogen we added earlier. So I added that hydrogen just to show you where it's going, so you have to add it when it's part of the mechanism. But once it's on the molecule, you don't draw it in anymore because it's implied on a skeletal structure. So after that rearrangement, you can see that hydrogen is still there. I'm just not drawing it in. It is still there. It's just implied. You have to see it with your mind rather than your eye. This third methyl group has moved over. By doing so, this carbon is now missing electrons, and it has a positive charge. And I've just made sure that these methyl groups here point to the end of a triangle because all carbocations are trigonal planar. So I'm trying to mimic the three-dimensional shape in 2 dimensions. Okay, so to review, first step was proton transfer. The hydrogen went to the less substituted carbon. That was Markovnikov addition. Then we had to check. Because we had a carbocation, we had to check for rearrangement, and we had it. And now that we have rearrangement, all that's left in this ring is a very clear nucleophile and a very clear electrophile. And notice how that's what I'm calling them instead of specific things. Right? You could call this some type of carbon chain, you could call this some type of chloride ion, but what you want to think of in these mechanisms, what you want to train your mind to see are conceptual units. That's what's going to stay the same as you go into future chapters, future courses. The specific molecules are just always going to change, but the conceptual units will stay the same. So here we have a very clear nucleophile, a very clear electrophile. How are they going to react? 95% of reactions happen because opposite charges attract. So the electrons on the nucleophile are going to attack the carbon or the atom that has the positive charge. So that's nucleophilic attack. And what that's going to do is add that chlorine onto that molecule. So when you're redrawing these, you copy everything and you only change things that are touched by that curved arrow. So this positive charge isn't going to be there, and then this chlorine is going to be bonded to, and actually here this chlorine is going to be bonded to that carbon. And you'll notice I had it attacking from the top, and now I'm drawing it from the side. That doesn't matter. It doesn't matter where you draw this because this sigma bond can rotate. And as it rotates, each of these is going to change position, like you're spinning an umbrella. So the chlorine will shift from being in the middle to being on the top to being on the bottom. And these things rotate at unbelievable speeds. Around 10 trillion times per second it can rotate. So that's more than we can conceive of. So what we experience is the average of all that. And so when you draw it, it doesn't matter where you put it. So this is the overall mechanism. 3 steps. You'll always have the proton transfer. You will only have the carbocation rearrangement if there's a more stable place nearby, and you'll always have the nucleophilic attack. The name for this reaction is hydrohalogenation, because you're adding a hydrogen, hydro, and a halogen, halogenation. And you can see it's Markovnikov addition, and you can have rearrangement.